So this is our presentation for CS372, and the main topic of discussion is going to be the key software engineering concepts. There's going to be three main things that we're going to cover over these slides. The first one being the importance of architectural design, distributed software engineering, and service-oriented software engineering, and how they important are as how important they are as concepts. The first topic is going to be architectural design, and the four main things that go into that are the design decisions, the different views that you can take, and the common patterns that are used in architectural design, as well as the usage of having these different architectures and what applications that they can serve in. So for the first one, the importance of making good architectural design decisions is that it establishes a foundational framework which dictates the software structure and organization. And this is really important because if you have an architecture that is formidable from the beginning, later on it allows it to become more scalable, and it can adapt to it can adapt to like product needs, environment needs, and the different development. And it also is very important for system efficiency, where if you have a very strong design architecture, then it allows for further development. And some of the more important decisions that are made during the architectural design process are that you can determine the application's nature, and you decide on whether an architecture is going to be distributed versus centralized. And a good example of this is like a traffic control system, where traffic controls as a topic, or traffic control is complicated on its own, as in there's a lot of dynamic processes that are going, but the architecture around it, which is old, they use very simple means of gathering this data, like just literal counters. So that was just a bad design, an architectural design from the beginning. So if it was a distributed system, you can collect a lot more data and more efficiently. And this shows you the importance of architectural design and the decisions that you make, because you need a very adaptable architecture. Something that's rigid has different purposes, but it's not very effective. The next part of in architecture is the different views that can take place, and this is particularly important because it gives you a comprehensive understanding of the architecture and allows you to look at the architecture from different perspectives. One of these perspectives is the conceptual view, which looks at the architecture as very it looks at it from a very high level, and understanding each component as their own block and how they correlate with each other and what information they share. But it outlines the general structure and how each system is interrelated, and gives a very good macroscopic understanding of the system. This picture on the right side here shows an example of a structure. So it just shows how each component relates to each other, how they keep communication and whatnot. The next view that can be taken place, or you can look at architectural views, is the logical view, and this is one step down and looks at the system's functional requirements and the blueprint for its design. But on a simple understanding, it's just one step lower from the conceptual view to understand the processes a little bit more in depth. And then the process view, it illustrates the system's behavior during execution and during runtime, and this will show you how it's like a real test of how the system works, because it's in runtime. And the development view describes how the system is methodically assembled and managed on the development platform, offering insight into its technical organization. So this would just be like how the the architectural is actually supposed to work in like production. And another common another main point for architecture and the different design decisions that can take place are the different patterns that one would choose. So the two mentioned here are the MVC pattern and the layered pattern. For MVC, you would see yourself using it more so when you need to have a separation of concern, as well as making sure that the UI and the data are separate from each other. So from here, in order to change the model and in order to change information, the controller, which is responsible for communicating to the view and the model, talks to them individually and then updates accordingly. So this type of pattern is particularly important when there's multiple views of data that are needed, and the data management is distinct from the user interface. So the data and the actual like UI is separated, and this is really good because it allows for modular development, testing, and maintenance. And a good example of this is like really any video game, but a simple one to understand is like a game of Pac-Man. So when you play Pac-Man, the actual character is moving, but that's the view, but the actual data behind the scenes would be kept in the model module, and then the controller communicates between the two. And whenever a position of the Pac-Man changes in the model, it gives that information to the controller, and then the controller tells the view to update the position. So this is from this understanding, we can see that MVC patterns would be very good for like smaller scale projects, but for systems that need a lot more like rigid structure and there's a more emphasis on trying to have each module completely separate for each other in terms of security, in terms of functionality, then the layered pattern would be very good. And this is really suitable for evolving systems built upon existing structures and any system that really needs further development on. And the main benefit of the layered pattern, is that it makes sure that each of the layers are completely exclusive and independent, making sure that one layer doesn't have a major impact on the other. And an example of this could be like online banking systems, which are rigid in their structure. They need high level security. So something like an MVC pattern would not be feasible, whereas a layered pattern is much more suitable for that. But these are the two main common architectural patterns that we've seen. For the application architecture, how you would see yourself using the architectures, you could use it as a blueprint for the design process, which is very good because you can look at the different views. You have a different idea of where each layer goes, and it functions as a comprehensive checklist during the design stages, organizes and streamlines the development team's workflow, and this could be understood from looking back at the development view, and facilitates component evaluation for potential reuse, and provides a common lexicon for discussing different application archetypes. So the different uses, for example, there's many, but one could be like the transaction processing systems, and the other could be language processing systems. And that's all for architectures. The main topic is going to be distributed software engineering, and there's going to be the four main topics we're going to cover are distributed systems, what is client-server computing, architectural patterns for distributed systems, and software as a service. So distributed systems, what exactly are they? They're basically a bunch of independent computers that work together and appear as one single system. So it's abstracted like that, and they're often incorporated into blockchain technology, and because it's on the blockchain, it has higher security and it offers a decentralized structure. And they're very known for their robustness and resilience, and this just goes more into the security point. So historically, having distributed systems has been very costly, but with modern advancements, distributed solutions have been more accessible, mainly because the cost to build them has decreased, and this allows for a lot of companies to actually add distributed systems into their software. And distributed systems are particularly important because they offer a higher level of resource sharing, uh, concurrent processing because it's on the cloud, and because it's on the cloud, you potentially have more security, which has better fault tolerance. And an example of this, you will notice there's a pattern, is that an example of a distributed system could be BitTorrent file system, which uh which is a lot more secure, as well as any crypto coin payment processors like BitTorrent and Binance. Yeah, and another main point into distributed systems is that client server computing. Before we do that, it is important to have a general idea of the client server model. And the client server model is basically how a server gives resources to a client, which the client requests. So a client is requesting, and the server is responsible for how the information he gives back. And in client server computing, is good to understand it. It comes in four different layers. The first one being the presentation layer, which manages how the information is actually delivered to the client. And then the data handling layer, which manages data flow to and from the client, including data validation and web page generation. And the application processing layer, this executes the core business logic of the application, and making sure that the requests that the user gives are processed and the server makes functional decisions. And the last layer, which is the database layer, it kind of has it's like an overview of this entire overview of the layers, and it's responsible for data management, handling storage, retrieval, and transaction processing. This, as a whole, sounds very similar to layered architecture. So you could imagine client server computing could follow a structure like this. And there are very similar to how there's different design or architectural patterns for architectural design. There's different patterns for distributed systems as well. So the five main here that we're going to cover. The first one being master slave. This pattern is really useful for systems that need a high response, and and that need a high response and uh, that need a high response. And an example I can give is say for example for microcontroller projects, if you have some communication protocol between like a microcontroller and a sensor, if you use the master slave protocol, you're able to extract information quickly and get faster response times, and it's similar to that in distributed systems. And then another one is a two client server model. This structure particularly prioritizes security and makes a direct connection between the client and the server. And then the multi-tier client server is very similar to the two tiers. It just has more clients, and just developed for higher volumes of transactions. And another very common one, which is used a lot, is the peer-to-peer architectural pattern, which allows clients to actually exchange data, and there's no need for centralized mediation. And this is really effective because it kind of automizes and enhances redundancy, because the server doesn't have to compute the same thing over and over again. And then the last one is the distributed component architectural pattern. And this offers a modular approach, allowing for a dynamic combination of distributed resources and services for increased flexibility and scalability. And the last point being software as a service, and this is something we're seeing a lot more nowadays. And as a concept, software as a service is basically a model where applications are hosted by a service provider and then made available to customers over the internet. And some common examples looking at these pictures here are Dropbox, Google Workspace, Microsoft 365. Before, Microsoft had a service where they would sell their software at wholesale. So you would pay once, and then you would get all of the different products, whether it's like Word, PowerPoint, etc. But now, since they've kind of changed into the software as a service model, they have everything online, and then providing the service as a they're providing the service as like over a prescription. And there are a lot of advantages to this. One being that the company, or they have a lot of flexibility to delay decisions on where and how services are provided. So the user could be using their service, and then they could just still make changes and then keep updating, and then the user is able to access them rather than having to purchase a whole other bundle. And because it's distributed and they're offering it online, it allows the architecture to be dynamic and adds it allows the architecture to be dynamic and allows to add new resources whenever they're needed, whether it's like getting new updates and etc. And distributed systems, software as a service, they're very important because the system becomes a lot more scalable and then dynamically reconfigured. So this covers the two main topics, which are architectural design and distributed systems. And then the last section, my partner will cover that. Thank you.
Hello, I will be speaking about the service oriented software engineering. The four components I will be speaking about are service oriented architecture, RESTful services, services engineering, and service composition. Let's start off with service oriented architecture. The definition given is that SOA is a means of developing distributed systems with standalone services that may execute on different computers from different service providers. Uh, the role in building distributed applications enables the construction of applications by linking services from various providers using standard programming languages or specialized workflow languages. So basically, the idea of service oriented architecture is that um, the architecture as a whole should incorporate different services wherein the service as a like the business, or let's for example let's stay with the term app. Let's say we're making an app. In the app of there will be different services incorporated into the app to make it user friendly for the user. So so in SOA, the architectural pattern in software design is where the services are basically components, and so the architecture, the service oriented architecture, is talking about how the different components can be used together, and they all have modularity wherein they can be removed or inserted, and the application as a whole will take advantage of this and make for a seamless, user experience. There's some key concepts in service-oriented architecture. Um, it's the one of they are the ones that are important are facilitating distributed computing, interoperability, wherein each component can work on its own, or it can work together with different services. The modularity, which allows for the compartmentalization of different services, and also the reusability. Also, there's the loose coupling. So, AKA, it means that each service interacts with each other through interfaces, but they're not, dependent. They're not relying on different components or different services. So this allows for plug and play. Basically, you could add services, you could take away services depending on the use case that you want to provide. And also the service-oriented architecture also, takes into consideration the scalability. So some programs or some apps, for example, may not need the same server capacity, or the need to be able to sustain very high loads of people trying to access their servers. So service oriented architecture is crucial in building distributed applications, and it provides a flexible and scalable framework. Basically, it's the architecture, it's the framework that allows for different services that may even be distributed across various locations to work together seamlessly to achieve complex business functionalities. So the main example I would use for this to highlight how this works, service oriented architecture, is online banking, where a fund transfer service, a loan application service, a customer support service, or even a bill payment service. All of these services, they're interoperable, and they can fit together to come under the whole umbrella of a online banking application, for a bank. So it gives agility and adaptability to the business. RESTful services, they fall under SOA. They're a specific type of service that adhere to the REST architectural style, commonly used within SOA. RESTful services are commonly used within SOA. So the best way to describe RESTful services would be that, well, first it stands for representational state transfer, and the best way to describe it is an architectural style for designing networked applications. It relies on stateless client server communication models, and is considered a simpler alternative to SOAP, for example, which stands for Simple Object Access Protocol. SOAP is more of a protocol for exchanging structured information in web services. It's more rigid, and it's when it's in its setup. It's known for being protocol based. It uses XML for sending messages. It has built-in error handling, and it supports WS security. So these are all things that SOAP does well. It's very, very secure. It's good for high security applications. RESTful, on the other hand, is faster. It allows for more people to be using it, and each service in RESTful is considered a resource, and these resources are identified by URIs. RESTful services also use stateless operations. The client-server interaction is stateless, meaning each HTTP request from the client contains all of the information needed to execute the request, and no client context is stored on the server between requests. It uses HTTP methods like get, post, put, delete for performing such operations. And the formats can support RESTful services can support multiple data formats, including JSON and but JSON is the most common one. How Let's talk about how this plays into our example of the online banking. Uh, if it was using a RESTful, service, if it adhered to the RESTful service architectural style, the bank's online service, or the bank's online services, like for example, account management, fund transfers, bill payments, they could be implemented as RESTful services. Uh, Whereas in like each service, like viewing my account balance, making a transfer, and transferring funds, each one is a resource which is accessible through the URI. So RESTful services would be ideal due to their like simplicity, statelessness, and efficient use of bandwidth. So when there's like on the 1st and 15th of the month where people get their paychecks, server load could be very of the high utmost importance. So the use of JSON allows for efficient use of bandwidth. Um, SOAP. We already talked about SOAP. Let's move on to service engineering. Uh, Service engineering is a process, is a systemic process which allows for the approach to it's the basically approach to designing, developing, and deploying web services. So basically, the service engineering process, it starts with the requirement analysis. What do I need? What do the customers need? Like for example, for the online banking, I want transferring, I want to look at my funds, I want to apply for credit cards, I want to pay my bills, all of these things. So first you want to know what you need to do, what you want to do. What are the requirements I need, and what do I need to fulfill what I want, like what pro like what how many people am I expecting to use my service. So after you have all the requirements analyzed, you have the service design. You can start designing. Oh, I want this. I want to be able to transfer funds from this account to this account, and I want it to use I want to have like the UI to look like this. So basically, you want to design how they all work together. These services. And then you develop the services, you implement the services using appropriate technology, you get it all working, you develop the services, and then you have the testing. You have your early stage testing where, you can test the basic functionality, see if everything is working, and if everything is working, you could deploy the service. After it's deployed, you have the monitoring and maintenance of the service. Continuously monitoring the service for performance is important. You always want to know, like, if there's errors, if there's issues, you want to know immediately so you can work on a patch right away to fix the issues. And then also in the service engineering process, you have documentation and discovery, properly documenting, the different steps you got to, the different steps you used to get to the service, um, and like how to engage with the service for ease of use for like people who are going to work on it in the future. The goal of producing reusable web services is that it could be reusable, it could be scalable, and it's maintainable for people in the future or other people who may want to use the same service. And then we have service composition. Composition is a technique used in SOA, in service-oriented architecture, to build complex services or workflows by combining simpler services, which can be RESTful, SOAP-based, or other types of services. Um, uh, so service composition is workflow-based service composition. It's used to support like more complex processes. If there's a process you want to be able to have your consumers use, you want to use workflow-based service composition, wherein you want to define a workflow for how like each for like each step in the process, each service that makes up the process. So the steps for like the most common steps are defining the workflow. So I want to get a loan, for example. Okay, so the step one, login. Step two, click on that, like, what kind of loan I want. What credit card I want, for example. Which rate is the best for me. You know. Um, so to do, and then like after that you apply the application service, and then like the results service of your loan application. So defining like the workflow of the user. So like step one, step two, step three, step four, all the way to the end. You need to define the workflow. And then there's the service orchestration. This involves coordinating and managing the interaction between different services as defined in the workflow. So the different steps of a process, they need to be able to work together, and they all need to be defined in the workflow. Orchestration controls the process flow, invoking the right service at the right time and handling data exchange between services. Sometimes it may be possible to automate the business processes, and this can be done to keep it consistent and require as little human intervention as possible. So handling exceptions and business rules is another step or another part. And the final part would be monitoring and optimizing, the execution of workflows, to see if there needs to be any adjustments made if it's not efficient enough. So, for example, in our online banking example, the loan application process, the workflow definition would be, for example, the process starts with the customer filling out the application, goes through credit checks, approvals, and then the release of the funds. And if we were talking about it in the service orchestration way, different services are invoked in a sequence. A customer service, like a service for the customers, is used to collect application data. And then there's a service that checks the credit score, and then an approval or non-approval service, and then and then finally a service to like actually release the fund. So, there's the workflow definition and there's the service orchestration definition. These are the things that make up the workflow-based service composition. And so in each of these examples, the workflow-based service composition allows the bank to automate complex processes to ensure they're executed efficiently and consistently. So that was just talking about our online banking, example, how the service composition would work in this situation. And in conclusion, to conclude to conclude our presentation, let's conclude by saying that we talked about the three things. To summarize the three things we talked about, topics: the architectural design. Architectural design is like the framework, the standard, or like the structure. The architectural design is maybe the most important in all of software engineering. The architectural design decision, it may be the most important decision, because it's really like the framework. It's like really the floorboards for everything the pillars for what you want to build above. So things like the patterns like MVC, layered architecture to structure software, facilitating modularity, flexibility, maintainability. All of these things need to be, conceptualized. All these things need to be, considered when talking about architectural design, which architectural design you want to go with. And then we have the distributed software engineering and software as a service. We talked about, Mubashir talked about how distributed software engineering employs models like client server, various architectural patterns to enable resource sharing, fault tolerance, and scalability across distributed systems. And then I talked about service-oriented software engineering, where there's, how service-oriented architecture. Service-oriented software engineering, the architecture, SOA. It's a broad architectural pattern for building software systems that use services. One of those most common style for services is the RESTful services. It's a specific type of service that adheres to the REST service style. REST being representational state transfers service. And then we talked about the composition and how the composition is really a technique used in SOA to build complex services. So like how they stack together like a big process that contains different services and or workflows by so a big process, it can be split up in different smaller services. And these services can be in the style of RESTful or SOAP or and so on. So in the end, these three topics show how there's a shift towards like a more dynamic and a more service-based architectures that prioritize the user needs, the user experience, like how like the user, because in this day and age it's very simple for end users to be frustrated with and immediately go to a different program or different service that may be competing. So really, a user, the user needs should be prioritized. So these three topics talk about how they're prioritized, how these are different architectures prioritize these things, as well as also the business objectives of the people who are putting these services into action. And these, this gives a framework for how software engineering can continue to evolve and its capability to solve complex problems, and really how software engineering can keep users, happy, and how it can show the dynamic for service. It could show how dynamic and agile, and adaptable your service can be in the future. So thank you for listening to our presentation, and I hope you have a great rest of your day.